So in this problem, we have a weight of mass m, which is attached to a string and slung over a light pulley. The other end of the string is attached to a vibrator, which is vibrating at a constant frequency v0, and the linear mass density of the string is going to be given by mu, which is 2 grams per meter, and the distance between the vibrator and the pulley is given by big L, which is 2 meters. Now, when m is equal to 16 kilograms or 25 kilograms, then standing waves are observed in the string. But for any values of m in between 16 kilograms and 25 kilograms, no standing waves are observed. So in part A of the problem, we're asked to figure out what v0 is. So let's start off with our equation for the wave speed, which is going to be given by the wavelength lambda times the frequency u0. And that's also going to be equal to the square root of the tension force in the string divided by mu. So here, notice that the tension in the string is going to be caused by the weight of the mass. So the tension force is just mg, and that's divided by mu to give us the wave speed. Now, since mu0 is kept constant, mu is kept constant, and g is constant, then this means that the wavelength is going to be proportional to the square root of the mass of the wave. Now, in order for standing waves to appear, an integral number of half wavelengths must fit between the vibrator and the pulley, which means that our equation for standing waves to appear is going to be big L is equal to n times lambda over 2, where n is a positive integer. So this means that lambda is going to be 2 times big L over n, which is proportional to the square root of m. And since big L is constant, this means that 1 over n is proportional to the square root of m. So what this tells us is that n times the square root of m is going to be equal to a constant. So for any mass m, its associated number of half wavelengths that fit within the wave, which is given by rule n, that times the square root of m is going to be equal to a constant. So let m1 be 16 kilograms, and let m2 be 25 kilograms. So let's suppose that the number of half wavelengths that fit within the wave when m is equal to m2 is going to be n. So since no standing waves appear for values of the mass in between m1 and m2, then m1 and m2, or the number of half wavelengths that fit in the wave for m1 and m2, must only differ by 1. So if n is going to be the number of half wavelengths that fit in the wave when the mass is m2, then n times square root of m2 is going to be equal to the square root of m1. Sorry, I'm going to write that over here. Square root of m1 times the number of half wavelengths that fit within the wave when the mass is equal to m1, which is just going to be given by n plus 1. Since n plus 1 is just the next consecutive integer that is greater than n. So if we isolate for n plus 1, we get that n plus 1 is equal to n times the square root of m2 over m1, which means that if we isolate for n, we get that n is equal to 1 over the square root of m2 over m1 minus 1. And if we plug in our values for m2 and m1, we get that n is equal to 1 over the square root of 25 kilograms over 16 kilograms minus 1, which is just 4. So this means that for m equal to 25 kilograms, 4 half wavelengths will be able to fit between the vibrator and the pulley. So this means that nu naught, which from this equation is going to be wave speed over lambda, that's going to be equal to, well, we know that lambda is equal to 2 times big L over n. So 1 over lambda is n over 2 times big L. And V is just the square root of the mass. So for n, associated mass is m2 and then times g over mu. So plugging in our values for n big L, m2, mu, and g, we get that the frequency, nu naught, is equal to 5 over 2 times 2 meters times the square root of 25 kilograms times 9.8 meters per second squared, all over mu, which is 0.002 kilograms per meter. So our final answer for part A is going to be 350 hertz. Now in part B of the problem, we're asked to figure out what the maximum mass we can put on the pulley such that standing waves still occur in the string. So notice that since n times the square root of m is constant, increasing the mass is going to decrease n. Now since n has to be a positive integer, the minimum value of n is 1. So for the maximum mass that we can put on the pulley, we have that n is going to be equal to 1. So 1 times the square root of m. And that's going to be equal to a constant. So that's still equal to the n associated with m2 times the square root of m2. So we're going to call that n2 times the square root of m2, where n2 is the number of half wavelengths that appear when we put m2 on the pulley. So from part A, we have that n2 is going to be 4, and m2 is 25 kilograms. So this means that m is going to be equal to 4 squared times the square root of 25 kilograms squared, which is just 25 kilograms, which is just going to be 400 kilograms. So 400 kilograms is going to be the maximum mass that we can hang from the pulley in order to get standing waves to still appear in the string.